Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. In this video, we are going to solve a second problem based on to the metal oxide semiconductor field effect transistor. Here we are with chapter 6 of microwave engineering. As the microwave transistors are helpful for the applications having the microwave frequencies into the use, we have this chapter. So up till now, in this chapter, we have gone through the introduction to the bipolar junction transistors for the microwave use, along with the physical structure, the configurations, the operating principles, the amplification phenomena, power frequency relationships. After that particular device, we also address the heterojunction BJTs, the JFETs, the metal semiconductor field effect transistors, and the high electron mobility transistors, and now the MOSFETs. From the previous problem, we have determined few of the parameters with respect to this device. Let us have some more calculations for the new problem. So here a problem statement for the MOSFET is given to us. A certain n-channel MOSFET has the following parameters: L is equal to 4 micrometer, Z equal to 12 micrometer, D is equal to 0.05 micrometers, Vg is equal to 5 volts, M is equal to 1, Vth is equal to 0.10 volt, mu n is equal to 1350 into 10 raised to the power minus 4 meter square per volt second. Vs is equal to 1.70 into 10 raised to the power 7 centimeter per second. Epsilon suffix IR is equal to 3.9. In the part A, we need the computation of the insulator capacitance in terms of farads per meter square. This is the parameter we have also practiced in the last problem. We need to compute for the new type of n-channel MOSFET with the given details. In the part B, we need to make the calculations for the saturation drain current in terms of milliamperes. Next to that, we need to determine the transconductance in the saturation region in terms of millimhos. And lastly, in the part D, we need to estimate the maximum operating frequency in the saturation region in terms of gigahertz here. So we first of all identify the given details, the given parameters in the problem statement. So very first parameter, as per the given problem statement, we have the representation of capital L. So capital L for this device is nothing but the channel length. So I mention here channel length is equal to, the value is 4 micrometer. The next is of representation by Z. This is nothing but the channel depth. So the channel depth we have equal to 12 micrometers. After the channel depth, we have the another dimension that is represented by D and is nothing but the insulator thickness. So insulator thickness is having the value 0.05 micrometers here. After that, we have some voltages. The voltage denoted by Vg is nothing but the gate voltage. So gate voltage is equal to, the given value is of 5 volts. Along with, we have a constant represented as M is equal to 1. It is nothing but the doping factor. So doping factor in our problem is equal to 1. After the doping factor, we have another voltage introduced here, and that voltage is nothing but the threshold voltage. So threshold voltage for the device holds the value that it is 0.10 volts here. After the threshold voltage, we are provided the mobility value. The mobility value represented as mu n is nothing but the electron mobility. So electron mobility holds the value 1350 into 10 raised to power minus 4 meter square per volt second here. After this mobility, we have the velocity denoted here Vs. It is nothing but the electron velocity. So electron velocity into the given device is nothing but 1.70 into 10 raised to power 7 centimeter per second here. And lastly, we have the relative dielectric constant represented as epsilon suffix IR with the value 3.9. This is with respect to the silicon dioxide SiO2 here. So with these given details, we get back to the problem statement. So now we solve for part A for computation of insulator capacitance in terms of farad per meter square. Now the insulator capacitance for part A is denoted as C suffix I and computed by the ratio of epsilon suffix I divided by D. So we make the substitutions of epsilon suffix I as 3.9 into 8.854 into 10 raised to power minus 12 divided by 0.05 into 10 raised to power minus 6 in place of D here. So this ratio gives us the value of insulator capacitance as 6.91 into 10 raised to power minus 4 in terms of farad per meter square. I outline this particular value. So here we are covered with the answer for insulator capacitance. Now we require to calculate the saturation drain current in terms of milliamperes. Now the saturation drain current in the part B we denote by I suffix D for the drain and SAT for the saturation, and it can be computed by having Z in multiplication to C suffix I in the bracket Vg minus Vth. The bracket is completed and in multiplication to V suffix S here. So the values can be put there, that it is Z is equal to 12 into 10 raised to power minus 6. C suffix I we have computed, that it is 6.91 into 10 raised to power minus 4. Now we have the another bracket that has a difference of 5 minus 0.1 into Vs is 1.7 into 10 raised to power 5 here. So finally we obtained the answer 6.91 into 10 raised to power minus 3. So as this is the saturation drain current, it should be in terms of amperes. Asked in the milliamperes, we put I suffix D SAT is equal to 6.91 milliampere and outline the answer here. So here we are covered with the calculation of saturation drain current. Now we require the transconductance in the saturation region in terms of millimhos. Now we denote the transconductance for part C by small g suffix m and S for the SAT for the saturation here. So it is computed by Z in multiplication to C suffix I into the velocity V suffix S. So we make 12 into 10 raised to power minus 6 in place of Z, 6.91 into 10 raised to power minus 4 from the answer of part A into Vs we put 1.7 into 10 raised to power 5. So this multiplication results into 1.41 into 10 raised to power minus 3. As this is the transconductance, it should be measured in terms of moles, or we can also represent them by the inverted omega sign here. So here the required transconductance into the saturation region is represented as 1.41 millimos here. I outline the answer here. So now out of the 4 things to be calculated, 3 have been done. Now we require to make the estimation for maximum operating frequency in the saturation region in the range of gigahertz here. So here the frequency at the maximum value can be represented for the part D by Fm, and it can be obtained by the ratio of Vs to that of 2 pi capital L. So the substitutions to the next step gives us 1.7 into 10 raised to power 5 divided by 2 pi in multiplication to 4 into 10 raised to power minus 6 here. So this results into the maximum operative frequency to be 6.76 into 10 raised to power 9. So frequency should be in terms of hertz, and now I represent the required value in terms of 6.76 gigahertz here. So the answer is outlined. So this way we are covered with determination of all the values required for the given device here. By the next lecture we shall be addressing the another topic in the same chapter, that is MOS transistors and memory devices. I hope you are enjoying the learning of microwave engineering subject. For more details and the knowledge, you can subscribe to Ekeeda channel. Thank you.